Hey everyone. So we have now wrapped up a good amount of understanding what a quadratic is, what a parabola is, and now we're going to move into this idea of applying quadratics to other situations. So we know how to graph a parabola, we know how to solve a quadratic equation, but what does that mean? Well, in the next lesson, we're going to talk about real life applications like, projectile motion. So if we shoot a rocket up into the air, or if we throw a ball or anything like that, it's going to follow a parabolic path. We're going to talk about those types of things in the next lesson. But in this lesson, we're going to apply it to other things that we know, like linear functions, right? We're going to try and see if we can solve equations in order to find points on a graph specifically where two functions might intersect each other. That's called a system of equations. And in Math 1 or in Algebra 1, you talked about where two lines intersect, right? And there's three different ways to solve those types of equations. There's substitution, there's elimination, and there's graphing. Well, here we're going to talk about systems of equations that deal with parabolas, okay? So I'm going to give you one example, and then I'm going to give you one practice problem, and that's basically it. But before we jump into that, let's talk about what this could look like graphically. Let me go ahead and minimize the screen here so you can see what's going on in my lesson. But how many solutions could we have to a parabola and a line? In other words, how many different places could a parabola and a line intersect each other? Okay, so how many different places? Think about that for a second. Well, if I had a parabola and I had a line passing through it, I could get up to two different answers. Okay, I could have two intersections, one here and one here. But I could also have one solution. Okay, so that's two solutions. I could have one solution. So there's a parabola and another function, a line. These intersect at exactly one point. And by the way, this line is called a tangent line to this parabola because it intersects it at exactly one point. It just skims off of it. That's actually a pretty major calculus concept. Hopefully someday you'll get to see that in action in a calculus class. But there's one solution there. It is right where those two functions intersect. You could also have it to where the parabola and the line never intersect, right? In this case, we have zero solutions because this parabola and this line don't ever touch each other. So you could get two places, you could get one place, or you can get zero places. And so the whole lesson today is figuring out where a parabola and a line intersect each other. And we'll get cases where we'll get two cases or one case or sometimes none, okay? So let's go ahead and take a look at an example of this, okay? What are the solutions of the following system? In other words, another way to say that is where do the two graphs intersect each other, okay? Now we know that this first one is a parabola because the highest exponent is squared. We know that this second one is a line because the highest exponent is 1. We know how to graph a parabola. We know how to graph a line, okay? So let's go ahead and solve this graphically. There are two ways to solve a quadratic, two ways to solve a system of equations. The first way is graphically. So let's go ahead and take a look at that. In the first function, f of x, I want to graph that. Let me line this up a little bit better here. So I've got f of x equals x squared minus 2x minus 2. I want to graph that. So remember, we got to find our axis of symmetry. That's going to be x equals negative b over 2a. So that's going to be negative 2 over 2 times 1, which is 2 over 2, which is 1. So our axis of symmetry is 1. Then we take that and we plug it in. Now, we've changed the notation. Normally we call it y equals, and that's fine if you do. But really, we're just looking for f of 1. So that'd be 1 squared minus 2 times 1 minus 2. Order of operations, exponents first. So we got 1 minus 2 times 1 minus 2. Then we do our multiplication. So that's 1 minus 2 minus 2. That's going to be negative 3. So here we have our vertex is 1 comma negative 3. Okay. So we know how to graph this parabola now, and forgive my very rough graph here. But I'm going to go ahead and graph this. I've got my vertex of 1 comma negative 3. So I'm going to go to the right 1 and down 3. Okay. Then I'm going to follow my slope pattern. So remember, I'm going to go up 1 and over 1. And then I'm going to go up 3, 1, 2, 3 over 2. And then I'm going to go up, 4 over 2, up 4 over 2. And then up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then over 3. Okay, so there is some points. I'm going to reflect it on the other side. Okay, and then I'm going to graph that parabola the best that I can. Okay, and notice I've identified some very clear points here. That's going to be important, okay, following the slope pattern. Now we have to look at our other function, g of x. So remember, g of x was x minus 2. So we should know how to graph that. That's just the line. And we would say that the y-intercept is going to be 0 comma negative 2 because of that last value. And the slope is just 1 because the m value is 1. So we're going to start at 0 comma negative 2. Let me go ahead and use a different color here. I'll use blue. 0, negative 2. And then we're going to follow the slope of up 1 over 1, up 1 over 1, up 1 over 1. And we can graph that line. So we have this line here. Okay. So we have this parabola and this line. And the question is, where do those two things intersect? Now we can see there's two places. They intersect here and they intersect here. What are those two coordinates? Well, this first coordinate is 0 comma negative 2. And the second coordinate is this one. So it's going to be 1, 2, 3, comma 1. So 3, comma 1. Okay. So that is our answer. That's our solution if we were to solve this graphically. Okay. We graph the parabola, we graph the line, and we look where they intersect. But notice it's so important that we graph it perfectly. Because if we don't graph it perfectly, and you can see a little bit of an issue right here, it doesn't look like they may be exactly hit right there. Something might be going on there, okay? So graphing, my point is graphing isn't necessarily the best way to get exact answers. It gives you ideas. But this is the graphical approach. You graph the parabola, graph the line, and see where they intersect. That's fine. The second approach is analytically, okay? So let me do that. Analytically means that we're using the equations. F of x equals x squared minus 2x minus 2, and g of x equals x minus 2. Now, how do we solve this analytically? Analytically means that we need to work with equations. Well, remember that f of x is equal to y, and g of x is also equal to y. So we could rewrite these as something like this. Y equals x squared minus 2x minus 2, and y equals x minus 2. Our goal is to figure out where this parabola and this line equal each other. So what do? We just set them equal. We say x squared minus 2x minus 2 equals x minus 2. We set this equation equal to that equation because they're both equal to y. So we set them equal to each other. Okay? And then from here, we solve this equation. Notice we have an a value, a b value, and some sort of c values. So our options are going to be factoring or the quadratic formula. Remember, to do that, we got to move everything over to one side. So in this case, we're going to subtract x from both sides, and we're going to add 2 to both sides. So now we get x squared minus 3x, and then notice the negative 2 plus 2 cancels out. So we're only left with x squared minus 3x. Now, I'm going to choose factoring because now I don't have a c left over, so it's just a and b. My GCF is x, and then my leftover would be x minus 3. Then we do our zero product property, so it's x equals 0, and x minus 3 equals 0. Well, conveniently, this one's already solved. I only need to solve this one, the x minus 3. So we're going to add 3 to both sides, and we end up with x equals 3. Now, what we would say is that these, let me go ahead and write this here, the solutions to this equation are x equals 0 and 3. But that's not my final answer, okay? These are the solutions to this equation. I want to know the solutions to this system of equations. Well, let's take a look back at our answer from our graph. Notice we got coordinates. We got one coordinate and another coordinate. Well, what did we find? We found the x values. Notice the x values match. X is 0 and x is 3. Okay? So what I need to find are the y values. So I got 0 comma something and 3 comma something. I've got to figure those y values out. Well, that's pretty simple actually. You can use either function to determine those y values. In the first case, I had x equals 0 here, right? X equals 0. So I'm going to take 0 and I'm going to plug it into one of those functions. F of 0 is equal to 0 squared minus 2 times 0 minus 2. Well, 0 squared is 0, and then minus 2 times 0 minus 2. Now we multiply 0 plus 0 minus 2, which is negative 2. So we know that f of 0 is negative 2, and so the coordinate that comes from that is 0 comma negative 2. Now, you may have recognized that you could have plugged it into the other function as well. G of 0 is 0 minus 2. That's negative 2. It's the same answer. It should be the same answer because we're looking for where these two things are together, what they have in common. So let's go ahead and find the other one when x equals 3. So we know this one is negative 2. Let's go ahead and find when x equals 3. So we'll plug in 3 to f. So f of 3 is equal to 3 squared minus 2 times 3 minus 2. And so we end up with 9 minus 2 times 3 minus 2, which is 9 minus 6 minus 2, which is 1. So f of 3 is 1. And as a result, we can write the coordinate of 3 comma 1. And that's exactly what we got when we solved this originally. So our solutions are 0, negative 2, and 3, 1. This was the graphical approach. And granted, I agree, I probably agree with you. You're probably saying that's kind of quicker. And I'll agree with that as long as we can graph the parabola nicely and graph the line nicely. But you need to know both ways. You need to know how to graph it and do it analytically, okay? So let's go ahead and take a look at another one here. You guys, this is your turn. There is your system of equations. Go ahead and pause the video and do it yourself and then see what you come up with and then push play, okay? All right, so let's go ahead and take a look at your problem here. You'll notice that h of x is written in vertex form, okay? So when we go to graph that parabola, that's actually going to be really easy to graph. It should be because that's vertex form is the easiest form to graph off of. But what I want to do is I want to solve this system analytically first. So let's go ahead and solve it analytically. Well, what does that mean? Analytically means we're working with equations. The question is, when does this parabola intersect this line? In other words, when are these two equations equal to each other? So we're just going to go ahead and set them equal. Okay, so now I have them equal, just like I did on the previous problem. But since this is in vertex form, I have to get this in standard form in order to work with it effectively. So remember, to do that, we have to expand the x minus 5 to say x minus 5 times x minus 5 because of the squared. Then we'll go ahead and multiply all that out. So we get x squared minus 5x plus 25, and then the minus 8. And then don't forget to carry down the negative 2x plus 5. And then because this has an A value, B values, and C values, we're going to want to move everything over to one side because we're either going to use the quadratic formula or factoring here. Before I do that, let me go ahead and combine like terms. I've got x squared. That's the only one. That's the only term with an x squared in it. So I got x squared. I've got negative 5x and negative 5x. That's negative 10x. And then I've got 25 minus 8. That's going to be plus 17. And then on the other side, we have negative 2x plus 5. And then we're going to move everything over to one side. So we're going to go ahead and add 2x and subtract 5 to both sides. And we end up with x squared minus 8x plus 12 equals 0. Now again, we can use the quadratic formula or we can use factoring. We should always try to use factoring first unless there's an indication that it's not going to work. So we're going to look for a GCF. The GCF is 1. So we go straight into the x. The top would be 12. The bottom would be -8. And the numbers at work here are going to be -2 and -6. Okay? Focus this a little bit better here. So then we'll expand this. It becomes x squared minus 2x minus 6x plus 12 equals 0. We'll group it. So the GCF here is x and then x minus 2. And the GCF here is going to be -6 because that first term there is negative. We take the negative down. And then the 6 is the GCF. Left over will be x minus 2. And then from here, we've got our factors of x minus 6 and x minus 2. Now we'll apply the zero product property. So we say x minus 6 equals 0 and x minus 2 equals 0. And we'll solve each of those equations. So we'll add 6 to both sides. We end up with x equals 6. Here we'll add 2 to both sides. We end up with x equals 2. Now, those are just the x values because I'm looking for the coordinates of where these two functions intersect. I need to find the y values. So I'm going to go ahead and plug those two back into my original functions. Now, if I did it right, if I plug in 6 to this function, I should get the same answer as if I plug in 6 to this function. So either one will work. I'm going to go ahead and plug it into g this time. So g of 6 is equal to -2 times 6 plus 5. So that's going to be -12 plus 5, which is -7. So one answer is 6 comma -7. And then the other answer, we'll go ahead and plug in 2. G of 2 is going to be equal to -2 times 2 plus 5, which is -4 plus 5, which is 1. So our second answer is going to be 2 comma 1. So these are the two places that these functions intersect, 6 comma -7 and 2 comma -1. Let me just double check my answers here. And that is correct. But now let's go ahead and look at it graphically, okay, and see if it makes sense. First things first. And graphing the vertex form. This is a parabola. Remember the vertex, let me bring it up here. The vertex of this parabola is going to be 5 comma -8. Remember, we change the sign of the inside and keep the sign of the outside. So that means we're going to go to the right 5, 1, 2, 3, 4, 5, and down 8, 1, 2, 3, 4, 5, 6, 7, 8. Ooh, this can get messy here. So I'm going to go up 1 and over 1. I'm going to go up 4, 1, 2, 3, 4, and over 2. I'm going to go up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then over 3. So that's that. And I think I'm going to stop there. But then I'm going to reflect on the other side. So this one becomes, that one's there, that one's there, and that one's there. So there's my parabola, or at least the points of my parabola. Go ahead and give me a rough sketch of this. Okay. And again, highlighting those points is going to make it a little bit easier to see. Okay. And then the next part is we need to graph this line. So remember, the y-intercept is 0, 5. So we're going to go up 5, 2, 3, 4, 5, and put a point. I should probably use a different color there. And then we're going to go according to the slope. The slope is -2. That means we're going to go down 2 over 1, and then down 2 over 1 again. Oh, look at that. We found 1. And then down 2 over 1 again, and down 2 over 1, down 2 over 1, down 2 more, and over 1. And we can keep going if we wanted to, but here's my line. And so now we can see pretty accurately here, not the greatest line, but we can see that this line and that parabola intersect at 2 points. They intersect here and they intersect there. Well, what is the coordinate of that first one? That coordinate is right 2 and up 1. And the coordinate of this one is going to be 1, 2, 3, 4, 5, 6, 6, and down 1, 2, 3, 4, 5, 6, 7, so -7. So those are my solutions graphically, and you can see that those solutions matched our solutions analytically. Again, you can't fall into the trap of just doing one or the other. You need to know how to solve graphically, but you also need to know how to solve analytically, all right? If you have any questions, please comment below or find me in a tutoring session. Otherwise, I will see you next time.